Okay, thank you, Mika, and good afternoon or good evening, everybody. So my name is Paavo Alku, and I'm professor of speech communication technology at the Aalto University. So my background is in signal processing and speech technology. And my talk today is entitled Glottal inverse filtering and its application in automatic classification of diseases. And I'll try to change my slide. Hang on. Okay, good. So this is the short contents of my talk. First, short introduction, and then I will very briefly describe glottal inverse filtering methods, not going into details and parameters. And in section 4, I kind of move to a bit more modern area of research, which is automatic machine learning based biomarking of health. And in section 5, I try to combine these glottal features into this machine learning area by describing a couple of our recent studies. And I finish my talk with short summary and conclusions. So let's start from the basics of inverse filtering. So glottal inverse filtering is actually a very kind of old research methods of voice and speech. And the technique is based on so-called linear source filter model, which is explained by this picture. So what we are interested in is the flow of air, which comes through the vibrating vocal folds. That's called glottal excitation. And we are given the speech signal, which is recorded by a microphone. And the idea is that we try to estimate from the microphone signal the source of speech, which takes place inside the larynx. And according to this picture, there are two filtering processes which filter the excitation, which is the vocal tract and then the lip radiation. The vocal tract is the very strong physiological filter caused by articulation system, and the lip radiation is just quite simple acoustical effect where the flow at the lips is converted into speech signal. So the idea, sorry about the messy picture, is quite simple. The computer kind of tries to estimate this second and third process. The filtering process is automatically from the incoming signal. And the key kind of problem is how to estimate this vocal tract part. And once that has been estimated, then the computer simply takes the input signal and feeds that through the inverse of the vocal tract model and inverse of the lip radiation model. In other words, the computer kind of cancels the effect of the formants and the lip radiation. And what comes out of this box, so to say, is a time domain estimate of the flow of air, which is used as excitation. So this is our target. And in this talk, and I would say that in most of our applications, we are really recording the speech signal outside the mouth. But as you probably know, it's also possible to use the so-called flow mask based on Martin Rothenberg's studies in the 1970s. And for instance, Johan Sundberg has done lots of studies by inverse filtering studies where he has used as input the flow signal. So in our case, we are using the free field microphone signal. And what is the reason for that is that we are interested in applications where we could do this inverse filtering from real life situations where, of course, one cannot use the flow mask. In general, this technology has a few benefits and, of course, some drawbacks. And benefits are listed here in the upper part. And what I would like to especially emphasize is the second one here is that inverse filtering, at least in principle, tries to estimate something which is a real phenomenon in voice production. So if you use, for instance, EGG, that's a wonderful method, but EGG signal electrocardiogram is actually a kind of artificial signal. It doesn't exist in the real speech production mechanism. Whereas our goal, the glottal estimate, is something which is real in human voice production. However, there are certain drawbacks, and I would say which are listed at the bottom part of this page. And the most severe one, in my opinion, is that every time a speech has high pitch, then the separation of the source and the track becomes more difficult. And typically, the estimate is not that good for high pitched sounds. But that doesn't mean that we couldn't estimate glottal sources from female speech as well. We can do that, but the accuracy is not that good. Inverse filtering typically, when it's used, consists of two different stages. The first stage is the use of inverse filtering technology. That means you record signals, sometimes 2 signals, sometimes 20,000 signals, and then every speech signal gives you the estimate. So if you have a lot of data, then you need to parameterize these estimates properly. And therefore, this analysis have the second stage where you select certain existing glottal source parameters and you kind of extract the most important information out of those estimated waveforms. So that's kind of background. And very shortly about the inverse filtering methods. I'm not going into any details here. I just want to mention that the first methods were really developed a long time ago at the end of 1950s. But still, even today, this is just a short list of some of the techniques. So you can see that there are known techniques published in the early 70s, and still even last year or year before, some new techniques have been developed. So there's an ongoing process, and a number of different techniques are still under development. What is shown in the boldface here is one technique which was developed about 10 years ago in my team, and this is a technique which we typically use nowadays when we need to do inverse filtering. And when it comes to glottal parameters, so these are the key numerical values which we typically compute. There are a range of different alternatives in this domain as well, because researchers have developed different parameters over the past 30, 40 years. And again, I'm not going into any details. I would just like to pick up the basic ideas. So these techniques typically work either in the time domain, which is the most natural domain, because the estimate of the glottal flow is in the time domain. And sometimes it makes sense to convert the signal into frequency domain. And when it comes to time domain glottal parameters, what different authors have developed are kind of straightforward numerical values which somehow extract those critical time instants of the glottal flow, and then certain quotients are computed out of them. So for instance, this picture here, the upper panel shows one glottal cycle computed most likely from my voice with inverse filtering. And what is worth actually noting here is that this y-axis, that's always arbitrary if we use free field microphone recordings. But if one has this flow mask, then calibrated flow mask enables having absolute flow values here. But in our case, this is always arbitrary, unless we use the flow mask. So that means that the wave shape is somehow needs to be quantified. And one possibility is just to compute these simple time quotients. Or then one can, of course, convert the signal to frequency domain, and the most inherent feature of glottal flow in the frequency domain is the spectral tilt. So one typically computes some kind of numerical values between harmonics, 2 harmonics, or number of harmonics, or one could fit some kind of nice function to measure the decay. But the spectral tilt or spectral decay, that's the most important frequency domain parameter which is quantified. So this is kind of background in inverse filtering. The technique is old. We have several alternatives for the inverse filtering technique, and then we can select the parameters. And once we combine them, then we can do basic research in voice production. But now I will move to this a little bit more modern part of research, which is how computer can be used to automatically detect diseases. And in this section 4, my idea is to give a very short general introduction on this topic. And then in section 5, I will add these Glottal features. So in this domain, which I call speech-based biomarking of health, this is actually a research domain which is becoming increasingly prevalent, has become increasingly important and prevalent also in the area of speech research during the past 5 years. And there's an increasing number of papers published in this domain, as you probably have seen. So the idea here is that given the fact that natural talkers use a range of different organs and physiological processes to create speech, if a speaker develops some kind of disease in some of these organs, then the acoustical characteristics of the speech signals change. So the idea is that could we develop data-driven machine learning-based techniques which could automatically detect these diseases. And the detection means that the machine needs to classify healthy people, machine needs to separate healthy talkers from pathological talkers, or then there are multi-class problems where you have a range of different diseases to be automatically identified, or one disease with several classes of severity which you would like to computer to automatically classify. But this is the background, and this is heavily data-driven area. So what kind of possibilities there are to build such systems? There are, in my opinion, two kind of approaches. The most the older one is called the classical pipeline approach. And when I said that something is old, it doesn't mean that this is not used. Actually, my team, which is working on this domain, mainly use this classical pipeline approach. And what is meant by classical pipeline approach is a system which looks typically something like this. So this is a flow diagram of a typical classical pipeline system where machine learning is used to detect diseases. And how the system works shortly is that we start with the database. We always, of course, need data. And data in this case means two things. We need the speech signal, and then we need something which is called medical labels. That means experts like you have studied, examined the patient, and have made the diagnosis and labeled the data. Okay, this is pathological with a certain disease, with a certain severity level, and so on. And then we have the recordings. And these two issues are combined with machine learning in this training phase. That means features such as glottal features later are computed from the speech signals, and then these labels are fed together into a classifier. And what is a classifier? Classifier is typically something which is shown here. It's very often so-called support vector machine. And to describe that easily, I have here shown a very simple low-dimensional space where these black dots are 8 speech samples produced by by patients. And then these white circles are 8 speech samples produced by healthy talkers. We are now in certain kind of acoustical space. And what SVM in the training phase does, it searches for this kind of red line, which is the optimal boundary between these two classes. And that boundary can be defined by optimizing the distance between two nearest samples of these two classes. And once this red line has been defined, when we use the system with the recorder speech signal, we convert that to features, for instance, glottal features, and then we kind of look on which side of this red line the sample happens to be. And that's the way, to put it simple, how the machine makes the classification. And what is nice here that everything is computed automatically from the speech input. And if we use inverse filtering, then we can combine into this and this block glottal features. So this is the idea. And an alternative to this classical pipeline system is this kind of modern so-called deep learning system. I don't like to use the word artificial intelligence because in my opinion, there's no intelligence in this network, to be honest. I use classical systems and end-to-end system. So what is the end-to-end system? It looks something which is shown in this slide here. The speech signal, which is in time domain, is typically converted into spectrogram. And then that spectrogram is filtered by a range of different neural nets, which are trained as a one unit, one block and one unit, rather than having this kind of separate feature extraction and classifier. So the difference is that this modern system kind of don't need a prior selection of the features, but computes these features internally inside these neural net layers. And what is the output? It's actually, to put it simple, either a green light or red light telling that, okay, this person was a patient or healthy subject. Okay, so that was the modern technology in general to use computer to automatically classify diseases. Two choices, the classical pipeline system or the modern end-to-end system. Okay, now the new section is that can we use glottal features with this modern machine learning classifiers? And the answer is that yes, this is possible, and that's something which we have done, and also some other research team have done. So I have here listed some of the articles which have classified certain diseases by using glottal features. I would like to say that those studies are not very many. My team has been doing some of them, but not all of them. Because we have kind of traditional background in this inverse filtering. So I will show you a couple of two examples of our recent studies where we have combined these glottal features in the automatic machine learning based classification. And this first study was published 3 years ago, where we studied automatic detection of heart failure. So this is not a very typical disease to be studied, because one typically assumes that heart has nothing to do with speech. But there is an indirect relationship. Some studies have suggested that when one develops cardiovascular diseases, the generation of fat causes swelling at the vocal folds. And we were interested that, okay, would we be able to show that there's a difference in the glottal flow computed by inverse filtering between healthy people and patients who suffer from heart failure. And I can show you one just example of a waveform. So this is again a bit messy picture, but let's look at this panel B and D. So all these curves are time domain curves, and this curve B is an estimated glottal flow which was computed from a healthy subject. And curve D is a estimated glottal flow computed from patients suffering from heart failure. And we can already here very clearly see that there seems to be a more smooth kind of rounded waveform in the glottal excitation for the patient compared to the health. So we use these features inside machine learning based classical detection system, which is as I showed previously, and this is a result. Let's forget the details. I just look at the two numbers which are shown here. So all the numbers here are percentages, which give the most simple metrics which is used in machine learning. It's called accuracy. So this 76 here means, to be this simple, that I have 100 people, half of them patients, half of them healthy ones, and the computer automatically makes the decision whether a person is a healthy one or suffers from heart failure. So 76 of them are correctly classified. And this is I would say it's not very good value, but it's something which is reasonably good and typical. What is important then that feature extraction was based on classical features. But then when we added these glottal features and changed the classifier, there was an improvement in accuracy, about 5 percentage unit. Not a very huge, but still something. And this is my message that this kind of trend has been seen in very many of our studies, that glottal features as such are not a miracle. But when we add them to some existing features, then they add some very useful information and the detection and classification accuracy improves. And in this case, there was some evidence that there has to be some kind of effect which takes place at the vocal folds. So that helped the machine to make the classification better. The other example is another article which was published a year earlier, and this is a bit complicated stuff, but I would like to kind of present it here. We were studying here 3 existing open databases. 2 of them had healthy versus dysarthric people, speakers, and third one had healthy versus dysphonic speech. And I would like to say that we have conducted also a number of studies on Parkinson's disease using a similar kind of approach. I refer to them, but I would like to more explain this study where we had these 3 databases. So again, we trained our system based on these existing databases. We built the classical pipeline system, and let's look at the results. My apologies that this is a bit complicated table, but let's try to see the forest for the trees. So what is shown here are, first of all, 3 existing databases. Not very large one, but open databases. And these 2 are quite famous databases on dysarthria. This is on dysphonia. And then we have metrics: accuracy, sensitivity, specificity. To put it simple, 100% in each of them would be a perfect machine. If 50% would be a toss in a coin, that means a chance level. So we are something between 50 and 100, okay? And then the interesting thing is here. We have these different features, conventional one, and then these inverse filtering based features. And what this seems to be a general result throughout these 3 database is that every time when we combine these inverse filtering based features with the existing features, the detection accuracy improved. So for instance, here, if you look at this guy here, 76% with the existing reference features, glottal features as such are not doing very well. They are giving a smaller accuracy. But when we combine these features, then the accuracy improves. And all these sort of bold numbers are the best ones. And all of them are kind of combinations where glottal features really help to some extent. But glottal features as such are not a miracle. Okay, let's move to conclusions. Glottal inverse filtering is an old technique which has been used for a number of years. And in my opinion, it's a very valid method to be used in voice source analysis in basic research. And there are a number of different techniques, and also what I didn't describe here at all, there are also existing tools. So if some of you happens to be interested in inverse filtering, we have both MATLAB code available and then this kind of standalone tool which was developed to be used by non-engineers. It's still we haven't been developing them during the past 5 years, but it's still, I guess, possible to be downloaded. During the past 5 years, my team and also other teams have combined this old area of research, glottal inverse filtering, with more modern machine learning based research of health, where the idea is to use machine to automatically detect diseases, classify diseases. And what are my sort of summarizing comments on this combination is that glottal features as such, I wouldn't recommend to use them as such in machine learning based detection of diseases. But as I said, if you combine them with any of the existing good feature sets, so most likely your system accuracy improves a bit because these features are very good in describing phenomena which take place at the level of the vocal folds. And when it comes to this speech-based biomarking of health in general, even though my research areas is in engineering and signal processing and machine learning, I must say that I'm very critical when it comes to these type of systems. I mean, end-to-end systems, which tend to be black boxes, which gives as output just green or red light. The signal is put in and what comes out is a green or red light. They might be very effective in terms of metrics, objective metrics, but I assume that clinicians like you are not that happy with this kind of black boxes. So what I would like to emphasize in our research is that we are very much interested in also providing explainability for these technologies. And in that sense, the glottal features are very useful. I mean, we should in parallel develop these black boxes, but also to explain that how certain diseases different from each other. And I would like to give you just one example of one of our studies where we were developing these black boxes. And then in parallel with that, we also showed that how two simple glottal parameters, so these two simple parameters have been developed by myself a long time ago, were able to very nicely distinguish two classes of patients. So in this case, these crosses are dysarthric patients with severe diseases, and then the black dots are patients with mild diseases. So instead of having green or red light coming out of the box, I think that this kind of representations are more useful. And this is something which we can get from glottal features. And then very final comment is that even though my team has been working mainly in glottal image filtering, so in the last 2 or 3 years, we have also conducted research in other domains of signal processing and machine learning. But our main research domain nowadays is really this automatic classification of diseases. But we are not relying only on glottal features, but only now and then we use them also have used them also this year and last year. But okay, and then I guess the rest of my talk is just a long list of papers. But yeah, that was everything I wanted to say. If you have any questions, so I'm happy to answer.
Thank you very much, Paavo. I'm sorry that I had to run for a moment, but the dog was barking, so I let him out. Otherwise, I couldn't hear you anymore. First of all, anyone else who has a question for Paavo Alku? Nobody. Paavo, what we tend to do in our biomarker committee as a first goal is to examine and to study a biomarker model for glottal closure. And why glottal closure? Because glottal closure is important not only for a good voice, but also for swallowing.
Yeah.
And we are imaging ourselves to the multi-dimensional aspects of voice. So are you familiar with the ELS protocol with the 5 dimensions of voice, which is perceptual analysis, visual analysis, acoustics,
Yeah, yeah, yeah,
aerodynamics, and self-assessment.
yeah.
So based on that, we believe that if we want to achieve a good biomarker model for glottal function, in caso glottal closure, then we should rely ourselves as much as possible on these 5 dimensions, and we should combine as much dimensions as we can.
Mm.
Yeah? But on the other hand, we want to be as practical as possible, so that people, in the end, that people could very easily perform a voice recording, for instance, on a sustained R,
Mm.
and that the biomarker rolls out of that. This could be a dream, of course. This could be perhaps impossible to do, because I understand that you are very much in favor of combining glottal features with other features, speech features. And this is the challenge we want to how do you say that in English? We want um, to take that challenge into hand. We want to make abstraction from speech, from articulation, um, from rhythm, and so on,
Mm.
for the glottal function.
Yeah. Okay. Yeah. Okay. So yeah, I want to say that in this talk, this is actually based on one of my previous talks. The key was on something which we are interested in, which is in machine learning, and there we combine. But this classical background, let's go to the early part of my talk. We are talking about something like this. This is still there. We can still do that, and we have technology to do that. And this is a kind of my main background. And to put it simple, if you have a good recording of your vowel R, then let's still go back to this picture here. Okay, this is possible, and your glottal closure can be characterized here with a number of techniques, and there's no machine learning here at all. You know, you don't need to combine any other stuff here, which I described in the later part of my talk. So glottal closure is something which is very much in the center of the glottal inverse filtering. And that can be parameterized with different techniques if that is something which you need. So in summary, if you have a recording vowel R recorded in a good enough microphone, it could be in principle to use inverse filtering to estimate glottal source automatically and then to parameterize the glottal closure phenomenon with different parameters. The only exception is that if you need to have absolute flow values, then that's a problem because absolute flow values need flow mask. I'm trying to develop by myself a technique to somehow combine these absolute values with free field microphones, but that's still it's not published anything yet. But yeah, my emphasis was a little bit too on this machine learning part, but this old stuff is still there, and
But
I
I
think
do,
that
yeah, sorry, I do think that your talk is very valuable, because what I am telling now is just the start of our biomarker committee. I can imagine that in the further stage of our biomarker committee that we will rely on deep learning or whatever
mm,
for other pathologies, for other diseases. Um, Another thing is that I wondered about something that Johan Sundberg told me. He gave me a presentation about sopran, and I think that your alto apparatus is a predecessor, or comes it after sopran, or?
yeah, I don't know what's sopran, but let's go to this. Is something this paper. reference list. Yeah, this 2017 paper, this auto apparatus, that's a free, you can download it freely, and you can do this inverse filtering auto automatically on that. And this is our most recent tool, and since 2017 we have not published anything. And the reason for that is very practical. Every time I have a good student who graduates and builds a system, then he leaves the university, and then big IT companies change the operating system, and then you had to start over from the scratch almost. And this is a very problematic situation, that developing these tools is needed, but it's very costly to kind of provide the support once the students have that. But yeah, this is our most recent application, and I don't know whether any of you have been downloaded that, but it should be able to use in ordinary
Yeah,
Windows system without any MATLAB
I have
installed.
downloaded Sopran, and I think this is Johan Sundberg told me that it is a bit similar.
Yeah,
Um, and am I right to say that with your Alto apparat we could have an idea of the glottal closure, but also of the maximal flow declination rate, which could be an aerodynamic dimension?
yeah. This is exactly now the issue which I mentioned, that if you want to have absolute values for your MVDR, I think that's the right abbreviation. I mean the peak derivative. Then you should have the flow mask, and in my opinion all the Johan's works are based on having a flow mask which is calibrated, and then it's possible to have it on absolute flow, absolute values. But what is still possible, and this is something which we have done in several studies, is that if you make your recordings with a constant microphone distance and with the constant gain settings of your system, then you can compare these peak values even with our system. But if you change the microphone or recording conditions and there's no calibration, then of course the system you cannot compare. So the flow mask, calibrated flow mask is it's very useful because it enables for you to compute absolute values. And that's something which Johan is doing all the time, in my opinion.
Okay, thank you. Ramon, do you have any questions for Paavo Alku? You mentioned another app, so I assume that you have something to say? We cannot hear you,
Yeah,
Ramon.
yeah.
Do you hear me? Yes.
Yeah,
Rather
Okay.
silently. Can you?
could it be a little bit more louder?
Can you hear me?
Yeah, now
Yes.
it's better.
Yes, yeah, now, okay. Well, better thanks, Professor Paavo, for your speak. I have not any question in this moment. I need to learn a little more that also lecture you give us. And but I in the committee of Biomarker committee, I have present an app of an engineer, Spain engineer, what have been work with inverse filtering and developed an app called voice analysis system that develop 22 parameters of the glottal closure based on this inverse glottal filtering. I don't know if you know about this app.
No, it's
We
interesting. I have not heard about, but if you have any links of that, so could you please send it to me, because I'm very, of course, interested to get to know.
Yes, of course.
Yeah.
Of course. Of
Good.
course.
Yeah. Oh yeah, thanks for that. Yeah. Okay. Any other comments or questions?
If not, nobody else. So if not, then we really thank you, Professor Alku, for your talk, for your insights. And perhaps we can work together someday. I don't know.
Yeah, if you have any questions, so feel free to ask me, and I'm happy to explain more. And yeah, and if you really are interested in inverse filtering, so hopefully we could provide something. And with these tools, so I has to keep in mind that, for instance, Aalto apparat tool, it's flexible, but when one starts to use it, there might be small bugs here and there. And this is my point, is that I unfortunately don't have anybody here to correct them. But basic research in inverse filtering is something which I'm very much interested in. I really look forward if there was some interesting data to help you. And but I want to say that please don't put machine learning in the same basket immediately. Work with basic research inverse filtering. That's much more useful in my opinion. And there are lots of community coming from deep learning with clever networks. But extracting features in Glottal, so that's a real thing. And that's the fun thing. So I appreciate that work. Yeah.
Okay. Thank you very much.
Yeah. Okay. My